Okay, so I think I already told you what the next topic is, but let me, if you don't remember, let it be a surprise because it does flow completely organically out of what we've been talking about before. So we obviously talked about electricity and magnetism, then the combination electromagnetism, which was what your homework 7 is all about. So let me suppose I have this thing here. I have some kind of conducting rod. And what I'm going to do is I'm going to apply some kind of AC source to it so that, of course, I can rapidly slosh charge back and forth. Okay? So let's talk about what would happen here. If you rapidly apply an alternating voltage source, sometimes this will be the high voltage and this will be the low voltage. So we're going to have plus charge on the top, minus charge on the bottom. You can kind of think of the rod as almost acting like a capacitor in some sense. This is an electric dipole which we have drawn the field for many times. So let me just remind you what that would look like. We haven't usually drawn it in up and down orientation, but the electric field looks something like this. It kind of has this lobey shape, etc. Don't want to draw too many of those. But I do want to point out that if you're out here on the side, it basically just points straight down. So if I were to be interested in the electric field right here somewhere, it might look like that at this moment. And then what's going to happen is as I slosh the charge back and forth, it's going to, of course, reverse the dipole, right? So it's going to reverse the plus being on the top versus being on the bottom, right? So if the plus were down here and the minus were up here instead, then the electric field would point the other way, okay? So it turns out that this is something we've never really acknowledged before, but it turns out that if we go out here, what the charges are doing, it does not register instantaneously, okay? So there is a time lag for information about the electric field to get from where the charges are to where we're looking in space. We've made no mention of that so far. Of course, we say that if you have this charge configuration that makes this electric field, we've never acknowledged that it actually takes time for that electric field message to travel to somewhere far away. So this is the first time where we're going to acknowledge that. The reason why we got away with that before is because it gets there so fast. It gets there incredibly fast. For us, there was no time lag before of getting the message from where the charges are to where the field is. So what we can do here is we can show what is it going to look like. I'll try to draw myself a little bit of a sketch here. If you oscillate the charge back and forth here, you're going to get that the electric field variations are going to go like this, up and down. These are the electric field variations, and they do travel. I'll call that speed v, with, of course, the electric field further away being older, that was made in the past, and the stuff that is over here is more recent, right? So the message about what the field is it takes time to get from one place to the other. So this is the most recent, and this is, of course, the older. So what electric field is registered out there farther away is not a reflection of what the charges are doing currently, but what they were doing in the past, okay? So what we have here is a wave, right? We have an oscillation of the electric field that's being sent out. So, change my marker out. So there's an electric wave. Now here's the thing, it's actually not just electric, because here's the thing, if the charge is sloshing back and forth here, of course, the only way the charge can slosh from one place to the other is with current, right? Current is the motion of charge. So if you have a current, sometimes it's going this way, and sometimes it's going this way, right? Sometimes it's going from the plus charge is flowing toward the top, sometimes the plus charge is flowing toward the bottom, right? So we know how to do that. We point our finger along with or thumb along with the current. The magnetic field over here is going to be going into the page when that's the case, and when the current's flowing down, the magnetic field over on the right side here is going to be out of the page. So there will also be a magnetic field variation flowing that is going to be going in and out of the page. So let me try to draw that. Maybe I can draw that in the different colors. So there will be a current sloshing back and forth, which will exchange. Of course, that's how the charges get from one end to the other and back and forth. And that will actually cause a magnetic field variation. And I've hopefully motivated why it's in and out of the page over here. That's just right-hand rule, so just like I just did. And from there, I'm not going to do the exact play-by-play, but here's what ends up happening. When the electric field is the strongest, so is the magnetic field. So it looks something like this. Let me draw it, I guess, here. When the electric field is strongest downward, the magnetic field is strongest like this. Okay? And when the magnetic field is, the electric field is strongest up, the magnetic field is strongest out of the page. It turns out when the electric field is going through zero, so is the magnetic field. So I can try here to draw in the intermediate cases. It's of course hard to represent the size of the vector when it's pointing in or out of the page, but I'm going to try by drawing it smaller versus bigger. Something like this. Okay? So this is the magnetic field. Now, what I'm really trying to draw here is basically there's like two waves. There's an electric and a magnetic oscillation going on simultaneously. This is what's called an electromagnetic wave, EM wave. Let me give you a few of the features, and again, I didn't justify this at all, but I'll tell you now, that Emax and Dmax happen simultaneously, so I guess I can say they co-occur. So when the electric field strength is at its largest, so is the magnetic field. And then the other thing that I can tell you is that there is a right-hand rule for orienting the three vectors involved here, electric field, magnetic field, and the velocity vector. With a right-hand rule number 1, if you slap E into B, your thumb gives the direction of the velocity of the wave. So let me give you an example. This, of course, we said that this wave was traveling to the right. So at any given point on the wave, we should be able to slap E into B and get to the right, because that's the way the wave is traveling. So let's try it out, say, right here. I slap E, which is down, into B, which is in, and that gives me to the right. Over here, I can try it. I slap E, which is up, into B, which is out, and still points to the right. So one of the cool things is someone can actually give you a picture of an electromagnetic wave and not tell you which way it's moving, and you can figure it out. Because if you take any point on the wave, slap E into B, your thumb will give the direction that it moves. So for instance, you might ask, is there only a wave going this way? Well, of course, there's stuff over here too, right? So we should probably draw it also over here, right? So what does it look like over there? It looks something like the same deal. It's a wave that travels out this way. And I guess let me not draw the whole thing because that's going to be annoying. I have to draw the whole thing out again. But let me at any given point where the electric field looks like that, let's say. So that would be like the corresponding point as to like here, right? So those are both points where the electric field is pointing up. Right? Remember that whatever is going on at any given time on this side is also going on this side, right? So they're both down or they're both up if you're talking about an electric field that was generated at the same moment, right? So over here, if we have that the magnetic field at this moment is pointing out of the page, well, that means the current's flowing down at that moment. Well, of course, if it's out of the page over here, it's into the page over here, right? So it'll be into the page over there. So the magnetic field at this moment is pointing opposite, and we can again try our slap rule, right? If we slap E into B, well, this wave is traveling to the left, okay? So, this is the first time we've acknowledged that information about the electric and magnetic field does not get instantaneously transferred to some point out in space. It travels as a wave. We'll find it travels very quickly, but it does take time. So this electric and magnetic field are not necessarily reflective of what the charges are doing at that moment. They're reflective of what they were going some time ago when this signal was actually sent. Okay? So again, you have the electric field that goes like this, and you have a magnetic field that goes like this. It's really kind of two waves in one. It's electric and a magnetic field simultaneously. I guess I should address what happens over here. This wave is not sent out in all directions equally. In fact, there is not really anything sent out over here. So the reason why is because if we look at the, so this is what's called a transverse wave. It's where the disturbance is perpendicular to the motion. So the motion is to the right. We have an electric field and a magnetic field variation that's perpendicular to that. So this is what's called a transverse wave. I talk about this in Physics 1, where the disturbance is perpendicular to the motion. In fact, here we have two disturbances, both an electric and a magnetic disturbance, which are both perpendicular to the motion and also perpendicular to each other. But you can't make a transverse wave along the same axis as they're oscillating. Okay? So for instance, if I had a clothesline that was horizontal, I have to move my hand vertically to put a wave in it. I can't move it horizontally too, right? I can't put a wave. Well, that's the problem we have going here and here. Okay? So you can't put a transverse wave in here because the motion of the charges is along the same axis as this itself lies on. Okay? So what we find is that the maximum signal will be sent out to the right, to the left, really anywhere in the plane that's perpendicular to the rod here, but not along the same axis as the rod. And for points off axis, you can probably imagine it's somewhat smaller. Okay? So if we wanted to kind of draw the distribution of the waves that are sent out relative to the rod, we get maximum sent out in the plane perpendicular to the rod. We would get nothing sent out here and here, and then we get smaller waves sent out off axis. Okay? So this is the max amplitude over here, the max amplitude over here, and then going from there. All right, so I've convinced you, hopefully, that if we oscillate charges back and forth, we can get this wave that travels. So the question then is, okay, what is this thing? Well, electromagnetic wave, another name for it is, well, other names for it, electromagnetic wave, also called electromagnetic radiation. Sometimes this is called dipole radiation because it's originating from basically a dipole charge configuration that's being oscillated back and forth. That's a very specific type of scenario where I'm producing one of these things. There are other ways to produce these electromagnetic waves. But the big catch-all for this is light. Okay? This is light. Okay? So our next whole topic is going to be about light, manipulation of light. And it's not a completely different topic at all from what we've been talking about. It's really the study of a particular type of electromagnetic scenario. It's a wave of it moving out, okay? So what we mean by light, of course, is not just visible light. Visible light is one particular type of light. So let's talk about the general properties of it. So first of all, we talk about its speed. The speed of light. Well, light is actually a wave that, unlike other waves, doesn't actually need anything to travel in. It doesn't need a medium. So that's very kind of a special thing. If we talk about sound waves need something to travel in, right? So sound wave that's going from me to you is a compression disturbance in the air. And if there were no air molecules between us, you couldn't hear me, okay? There is no sound in a vacuum. So when you see those clips of, for instance, like, you know, sci-fi movies where there's a spaceship out in space, you see the long shot where it's far away and then it explodes, you hear, poof, there'd be no way you could hear that. There's no air molecules in space between you and that ship. But you can see it just fine, just like we can see things out in space, because light waves don't need anything to travel on. They can travel through nothing. So the speed of light in a vacuum, which is nothingness, well, let's address that first. We'll come back later and address what happens when light actually has to travel through something. So light can also travel through stuff, it just doesn't need to travel through stuff. The speed of light in a vacuum, we usually use a special letter C. When we actually have light traveling through stuff, we'll switch back to V, good old V, but the speed of light in a vacuum is C. How do you determine it? Well, you can actually get it from our magnetic and electric constants. So mu naught was in every single magnetic field formula, and epsilon naught, or its cousin K, was in every single electric field formula. Remember when I told you these have these tantalizing names, the permeability and permissivity of free space? Well, they literally are the constants that will tell you how fast can an electromagnetic wave travel through free space. Okay? So the permissivity and permeability of free space are because they are constants that are used to determine what are the actual properties of a vacuum, of nothingness. Okay? And this value comes out to be 3 times 10 to the 8th meters per second, which is basically the cosmic speed limit. You can't have anything travel faster than that. That is literally how fast can the information get from one place to the other? How fast can the information about a field get from one place to the other? Okay, and it has no mass to carry at all. It's just information about what's going on with the charges. It's the cosmic speed limit. You can't go any faster than that. It's extremely fast. Okay, that's 300 million meters per second. Okay. For instance, you think about how far away the sun is. That only takes 8 minutes for light to get from the sun to us, okay? Even though it's millions and millions and millions of miles away, okay? So there's no way you would have ever noticed a time lag in how long it takes light to get from one place to the other, okay? But if you're starting to talk about astronomical objects that are extremely far away, what you're looking at is you're looking in a time machine. When you look up in the sky, you're looking into the past. Because what you're seeing is light that left those stars long ago and is just arriving to you now. Some stars that you may be looking at may be long since ceased to exist, but you're just now getting the signal of what was going on with it many millions of years ago. Okay? So, let me remind you of our good friend from Physics 1, which relates the speed of a wave to its frequency and wavelength. So in our case, C is a fixed value. And I want to remind you that if you go to a lower wavelength, you'll go to a higher frequency. So this is just a mathematical way of encapsulating the following. If the wavelength is smaller, which is that the crests of the wave are closer together, well then the frequency, which is how often they arrive, will be larger. If the crests are closer together, you'll see them more often. Okay? So that's what that equation says. Make sure you understand B equals F lambda. And let me remind you, I guess, of our units here. Of course, wavelength is 1 meter, is measured in meters, and frequency is measured in cycles per second, which is also known as a hertz. Okay? And cycles is not a real unit, so hertz is just another name for an inverse second. Okay? So, what I want to do now is I want to kind of split up. What we do is we take the electromagnetic waves of various frequencies and just make them into bins. This is called the electromagnetic spectrum. It's just taking the usefulness and applicability to human existence and putting them into artificial categories, whereas this really just is a continuous phenomenon. So let me make a little bit of a sketch of that. So let's write down the electromagnetic spectrum. And I'm going to write it down in order of increasing frequency and that, of course, means decreasing wavelength. So it would look like this. Okay. So let me give you some rough boxes. The first box is radio and TV waves. Okay? So these are on the order of 10 to the 6th to 10 to the 9th hertz. Again, it's just rough orders of magnitude that these boxes are defined. So there aren't necessarily any definitive cutoffs because they're just arbitrary anyway. If you calculate the wavelength of that, wavelengths of those are in the kilometer to centimeter range. Okay. So if you use V equals F lambda to compute what wavelengths those would correspond to, you'd get roughly those wavelengths. So these have obvious uses for humans for communication. Okay. So the rod that I drew before, that I was sloshing charge with, what was that thing? So if I put a rod on top of a TV station and I oscillate charge through it and I send you a TV show, what is that rod called on top of that station? It's an antenna, right? And by the way, remember we talked about that antenna, it sends out stuff not necessarily all symmetrically, so there are dead spots to an antenna. It does not send stuff out equally in all directions. Okay? So if you notice your reception being better or worse, it's because you may be in a dead spot. Okay? So the next box that we usually denote, microwaves. This is roughly 10 to the 9th to 10 to the 12th hertz. And if you compute the wavelengths that are associated with that, you'll find they go from the centimeter into the millimeter range. These have obvious uses for microwave ovens, right? These aren't particularly high frequency, and it's going to turn out that frequency is tied to energy. We'll learn later on. So there's not a lot of energy in these things. microwaves just happen to have a little bit of a special relationship to water. So you may be well aware that if you put something in the microwave oven, like just an empty ceramic dish or something like that, it's not going to heat up, right? Okay. Next category, we get to infrared, which starts at about 10 to the 12 and takes us up to about 10 to the 14th hertz. That takes us from the millimeter range all the way into the high nanometer range, and includes, by the way, all of the micrometer range. This has a special relationship to us because it turns out that if something is at a temperature that is around where we live, so not super, super cold, not super, super hot, but generally around the temperature range that we live, well, temperature is a measure of thermal motion, right? It's how much the atoms are jiggling around. Well, atoms contain charges, and charges are jiggling around. So if charges are jiggling around, they make electromagnetic waves. So the fact that you are not at absolute zero means that you are giving off infrared radiation, okay? You may not be able to see it. If you walk into a dark room, no one can see you, but if someone's wearing some heat-seeking goggles, right? Maybe you're running from the cops, okay? You have a helicopter chasing after you with an infrared camera, they can see you, right? This is how they find you hiding in the bushes, because you're giving off some kind of signature, and that is infrared radiation. So this is how we generally, what we experience infrared radiation as is heat. If something feels warm, it's because it's giving off a lot of infrared radiation, okay? So then we get, of course, to the very special narrow sliver of the electromagnetic spectrum. If it goes into your eye, then you can experience it, your brain can interpret it. That's visible light, okay? This is not some several orders of magnitude here. This is a very thin sliver from 4.3 to 7.5 times 10 to the 14th hertz, which is, if you want to express it a little bit more nicely, 430 to 750 terahertz. Okay, tera is 10 to the 12. Okay. So that's in order. That's the frequency, and of course, if the frequency is increasing, then the wavelength will decrease. This is 430 terahertz is 700 nanometers, and the high end of the frequency is the low 400 nanometers. We experience this as color: red, orange, yellow, green, blue, violet. Classic Roy G. Biv. You can put an I in there for indigo if you like, but I have no idea what color indigo is, okay? Of course, you can split this up much more finely, but that's about all the major colors, okay? I'm not going to argue what's the difference between emerald and teal. I think they're both green, right?
I was going to say, I think in photography and printing, they just use RGB.
Oh, well, the thing with that is that you can actually combine, mix them too, right? So you can get different colors out of just some basics. The red is, of course, right next to infrared, and violet, the next category, is ultraviolet. Okay? So as we're increasing frequency here, we are increasing the energy, and these are going to start to sound a lot more like things you don't want to be experiencing. Okay? For instance, if you spend too much time out in the sun, you get too much UV, there might develop some skin cancer, right? So we are moving into the higher energy, and we start to move into what's sometimes called ionizing radiation. Okay? So ionizing radiation is radiation of a high enough frequency that they could potentially cause some harm. There's too much energy in there, okay? But anytime someone tries to tell you that all radiation is harmful, you can point out you couldn't see a thing without radiation, okay? So not all electromagnetic radiation is bad, just starting to be high frequency ionizing radiation. And I want to point out that microwaves is way down here, okay? So if someone tells you you're going to get cancer by standing in front of a microwave oven, they don't have even the basic understanding of physics, okay? Okay. Now, you think that's crazy? I've heard medical doctors say that, okay? So just because they went to medical school does not mean that they have grasped the basics of physics, okay? So, UV. That goes from the end of the visible range, of course, up to about 10 to the 17th hertz. That brings you from the end of the visible range all the way down into the low nanometers. So those are those wavelengths. And as we go up here, of course, we're going to see other categories like X-rays. Just like you don't want to spend too much time out in the sun, you really don't want to hang out underneath an X-ray machine for very long. Right? This is where we start to seriously monitor how many X-rays have you had in a year so that you don't get too much exposure. This takes us from 10 to the 17th up to the 10 to the 20th hertz. And that will bring us down into the picometer range. Okay? So starting to perhaps be some of the prefixes that are so small as to be uncommon. Pico, that's 10 to the minus 12. These are all, by the way, on the equation sheet if you don't have them all memorized. And then everything from there up is what we call a gamma ray. Okay? So not something you're liable to encounter in everyday life, but as a recommendation, don't hang out inside a nuclear reactor either. Okay? That's where you start to really have very high energy situation. So that's anything basically beyond 10 to the 20th hertz. Okay? So that starts picometer and then lower. Okay? Question?
If you don't mind me asking, you talk about radiation from flying an airplane at 40,000 feet.
Mm-hmm.
Where does that kind of...
that tends to be starting to get into the UV, right? The idea being is that if you don't want to be lying around the beach too much because you're going to get that from some of that from the sun, you have even less protection if you're, say, in Denver, the mile-high city, or even higher in an airplane, just because you don't have as much air between you and the sunlight that's coming in. The air can do a little bit to kind of absorb some of that radiation. So that's what you're really kind of worried about when you are, not even necessarily in an airplane, but just going very, very far above sea level. So they tell you, wear your sunscreen when you go to visit Denver, right? Because you're going to get a much worse sunburn for an equivalent amount of sun exposure. Okay, so you can see this is immensely useful. These are all just categories, right, that we're breaking up. They all just kind of fit the pattern of being about 3 orders of magnitude, right? 6 to 9, 9 to 12, 10, 12 to 14, 14 to 17, 17 to 20, right? And that's because someone just at some point just decided that would be a nice way to just kind of break up into boxes. But it's all the same stuff, electromagnetic waves, okay? Are there any questions so far? Okay, so the next order of business here is we're going to start doing a bunch of light topics. And the very first one I want to do is something called polarization, and I'm going to focus on this because your lab next Tuesday is going to be on this. And so I want to get you prepped for it. And so let's talk about polarization. So here's what polarization is. We talked about the fact that we have a wave that might go like this. So the electric field might oscillate back and forth like this. I'm going to omit the magnetic field because the magnetic field is, of course, generally pretty much nailed down once you know the electric field. So it might be moving in this direction, and it might have that orientation to the electric field. So that's basically, I've sloshed the charges up and down. I've created an up and down electric field variation, and it's traveling outward. As a shorthand, I might just draw it like this. So I just want to show the plane in which the electric field oscillates and the direction of the wave. That just saves me some writing. This kind of light is called linearly polarized. And specifically, it's vertically polarized. Because the electric field is vertically oscillating up and down. Now, I don't have to shake the charge in an up and down orientation. I can shake the charge sideways, right? And if that's the case, the electric variation will be sideways. So I could also try to draw, not a good drawer, but I'll try to draw it in kind of 3D. The electric field oscillation could be sideways. That's supposed to be a right angle. That's not a good drawing. I hope maybe you can do better. But I'm trying to draw this, right? So the electric field oscillation is in the horizontal plane. So this is horizontally polarized. So basically, polarization is just a way of describing along what plane or what axis is the electric field oscillating on. It could be oscillating vertically or horizontally or diagonally, right? My drawing looks more diagonal just because I can't draw, but it's supposed to be horizontal. So you can have linearly polarized light that's vertical, horizontal, or even diagonally. I could have a wave that's like this, right? So that would be a diagonal polarization. The electric field is oscillating along a diagonal. I could also have something which is called unpolarized. So this is unpolarized light. So you could have, unpolarized is a little bit of a misnomer. It's really all polarized. It has all the polarizations in it. So I guess the reason it's called unpolarized is because it doesn't have any particular preferred thing. Now how would you create this? Well, you'd have to have a bunch of charges oscillating in all different ways. So you have some light in there. Some charges are oscillating vertically and creating vertical polarization. Some charges are oscillating horizontally, creating horizontal polarization. Other charges are oscillating diagonally, getting diagonal polarization. So you got everything in there in equal amounts. Okay? For instance, the light from this light fixture. Okay? That's created from a large number of charges all oscillating around in willy-nilly ways. There's no reason to think that we would get any particular polarization out of it. Okay? So, the next thing I want to show you is that once you have one of these types, you can manipulate the polarization. So what we do is we talk about a polarizer. So this is one of those funny things where I might talk about, okay, where do you see this in nature? That's not what I'm going to do here. I'm literally going to talk about a patented, or I think it's patented, perhaps the patent right now, but this is actually developed by a company, developed by Kodak. You may have heard of the Polaroid camera, okay? It is a manufactured piece of material that can affect the polarization of light. And I'm going to start there. This does have some place in nature as well, but I want to start here. So it's literally some piece of material. I usually draw it as a circle for no apparent reason. You can make it in whatever shape you want. In fact, what you guys will use a circular shaped piece of material in lab, but I have squares here. Okay, so these are square sheets of polarized material. So let me talk about how they're made. They're actually made by running a series of polymers in these long strings that. So while you can't tell by looking at it, it's actually constructed out of a highly asymmetric chemical structure. Okay? There are long lines of polymers running one direction only. Okay? So obviously you can't manufacture it perfectly, but that's what they strive for. I like to think of this as a light harp. So you guys know what a harp is, an instrument, right? Bring, you run your fingers across it. So if we went up to this and pretended it was like strings of a harp, if we went like this, it would play, right? But if we went like this, we'd just be scratching the strings. So just like there's a harp where there's a preferred orientation where you can pluck across the strings and get a sound or a wave, and if you pluck with the strings you don't get anything, that's exactly the same thing here. So what you find is that if you try to send in light that has this polarization, that's with the strings, that gets blocked, and an ideal polarizer, none of it gets through. And if you, so that I guess I'll say 0% is allowed, whereas if you sent in something like this, that's the right orientation to pluck the strings, and 100% gets through. Now, of course, whether that ideal can be realized in actuality is how good are you at manufacturing these, the chemical composition perfectly. No real polarizer can live up to this ideal, but this is basic physics. We'll assume we have this polarizer that can do this. Okay? And in fact, what we sometimes like to do is we like to mark the axis along which it will allow things. So this is called the transmission axis. Transmission axis, or sometimes TA for short, and that's usually the only thing we bother to draw. We don't bother to actually draw the chemical structure of it. So we just generally like to draw a transmission axis, and we just then can remember that if the polarization is lined up with the transmission axis, it will get through. If it's perpendicular to it, it will get blocked. Okay? So let's go ahead and try to analyze what is it if we have some kind of diagonal thing. What is it that if we don't have it perfectly lined up, or we have it perfectly not lined up, we can of course have some intermediate case. So let's talk about that. We'll put in our polarizer, we'll put in our transmission axis, and then let's have a light beam coming through that is diagonal like this. So again, we have a vertical transmission axis like this. So let's say it's vertically up and down. And we have not a light wave that can get straight through like this, which would be perfectly aligned with that vertical transmission axis. Not something that's coming in like this that would perfectly get blocked, but something that is diagonal like this. Okay? So let's sketch in here. At a given moment, let's say the electric field comes in like this. So this double-headed arrow that I've been drawing, of course, is representative of the fact that it oscillates first this way, then this way, then this way, but at any given moment it's going one particular direction, right? So what I do is I go ahead and I break this electric field into components. I basically think of this as a combination of something that will get blocked and something that will be allowed through. I break it up into two components like this, E parallel and E perpendicular. Okay? So this is the beauty of components, right? Is that you can take something which is somewhere in between in the gray area, you can break it up into pieces, each of which has a definite action from the polarizer. What we find is that this component, of course, is blocked, and this component is allowed through. So what we have coming out is E parallel. Okay? So what went in was E, and then not all of that E got through. E parallel, only a part of that actually made it through, the part that was aligned with the transmission axis. Okay? So this is the input, and this is the output of the polarizer. So, of course, normally with components, let's go ahead and do our SOHCAHTOA. So let's say that this angle between the incoming polarization and the transmission axis was theta. Then how could we express E parallel? What is it? E cosine theta, that's right. So E goes in, E cosine theta comes out. It's reduced. And how reduced it is relies, of course, on how big of an angle do you make to the transmission axis. You can try it out here, of course. If you don't make any angle with the transmission axis, then what comes out is just E, right? Cosine of theta is 1. So that would be E gets through. E parallel is the whole thing. 100% gets through. Or you can try 90, right, where E parallel is going to be nothing, right? Cosine of 90 is 0. Or anything in between, right? The cosine of theta just provides how much is let through. This angle can range from a minimum of 0 to a maximum of 90. Everything else after that is a repeat. And I mention that because the lab, I think you rotate it through 180 degrees. But 180 degrees, well, if you're lined up and you rotate something 180 degrees, you're still lined up with the transmission axis. It's when you're 90 degrees that you're perpendicular to it. So that's the basic action of a polarizer, is that it generally can chop some or even all of the electric field. And if something does make it out, its polarization is changed because it came in diagonal, but now it's vertically polarized because, of course, that was the only part that actually got through because it was a vertical transmission axis. So remember that what comes through is not only reduced, it's also aligned with the transmission axis that it just came through. So what we have is it's a reduced total magnitude, and also it is aligned with the transmission axis, so the output. So the overall size of the wave is reduced, and whatever does make it through will be the part that was aligned with the transmission axis. The polarizer, in some sense, can rotate the polarization as well as reduce its size. Now, this is all well and good, but there's something that I have to tell you. If you're talking about the size of the electric field, that is not actually, for instance, for visible light, what our eye measures. Our eye measures something a little bit different. And in order to remind you of this, or in order to motivate this, I'm going to remind you it was the same deal at the end of Physics 1. So let's talk about sound versus light. So for sound, let's talk about frequency first. What's the frequency of a sound tell you? How do you experience frequency?
Bass.
What's that?
Bass.
Oh, bass or treble, right? It's a pitch. Yeah, exactly. So if it's a high note or a low note. What's the frequency of light tell you? What's pitch for your eye?
Color.
Color. Right, Roy G. Biv. So color is like a musical note for your eye. Or I guess you could say that sound is like color for your ear. Okay? What was the other quantity for sound that we might be concerned with? Not just as pitch, but also what? Volume or loudness, right? So not just if it's a high note or a low note, but if it's soft or quiet or loud. Does anyone remember from Physics 1 what quantity measured that? Was it the amplitude of a wave directly? is a property called intensity. Its units are watts per square meter. A watt, right? Joule per second. We've used that a lot more in this semester, right? Energy per time. So how loud a sound wave is literally how much energy per time it exerts on a particular area, right? So for your area is the eardrum, right? So it's the amount of energy arriving per time. So the intensity is energy per time per area. And one of the things that we did in Physics 1, I didn't even give you the formula for intensity, but I did tell you it was proportional to the amplitude squared of the sound wave. So for instance, you can say things like if the amplitude doubles, then the intensity is 4 times, right? I gave it only as a proportionality. I didn't actually even give you the formula. Well, intensity, same deal over here, okay? So this is the brightness. Okay? So how bright or not bright has to do, a light has to do with the intensity, the energy arriving per time per area, this time on the back of your eye instead of your eardrum, okay? So, of course, you might say, oh, ow, that light is too bright, instead of, ow, that volume is too loud, okay? So, think of it like brightness is like loudness for your eye, right? Sometimes you might even say that's a really loud shirt if it has a weird color, right? We tend to kind of mix these things up. These are all sensory inputs to our brain. Sometimes you hear musicians talking about the color of sound, right? So the brightness is proportional to the amplitude squared, which in this case is the electric field amplitude. So we're in the same boat. These are all just waves after all. They're just different waves that go into various orifices in our head. Okay? So over here, I want to convert this over to, instead of talking about E, which is the amplitude, which we don't directly measure, I want to talk about I. So if E is reduced by cosine, then we go to the proportionality, and I will be reduced by cosine squared. So here we arrive at what's called the law of Malus, which is this. It tells us how the brightness of light on the way out of a polarizer will differ from the brightness going in. And the factor that it's reduced by is cosine squared of theta. This angle can range from 0 to 90. Again, just to remind you, just so you have it all in one place. And I also want to point out to you that the angle that is appropriate putting in there is between the transmission axis and the incoming polarization. That's what you're trying to measure with that angle. So how different is the light that comes in angled from the transmission axis, which is the axis that allows the light. Okay? The more different it is, the less will be let through, and of course, at 90 degrees, nothing will be let through. Cosine of 90 is 0. The other thing that I do want to put here, because this is something that students often forget, is don't forget that the outgoing light is not only reduced in intensity, that's right in the formula, but also the outgoing light is parallel to the transmission axis. So it's not just a matter of reducing its amplitude and intensity, it's a matter of actually rotating the polarization. So that right there, what's in that box, is kind of like your master equation for working with a polarizer. Okay? The one thing that we have to do before I just go ahead and show you some examples and knock out some, do some examples on the board and show you some demos, I have to address unpolarized light. Because then you might say, how do we measure the angle between the transmission axis and the incoming polarization if you have all these different incoming polarizations? So let's take care of that. Any questions before I even do that? Yeah?
Isn't this how modern day 3D glasses work?
Yes, so I'll talk about 3D glasses as well. So let's address what happens when unpolarized light goes through a polarizer. Well, you've got a little bit of everything in there, right? So if this is the intensity of the light that's coming in, it's a little bit unclear what angle to put in there. But let me suggest to you that maybe we should do some kind of averaging, right? So whatever theta we should put in here, it should be some average angle that the light that comes in makes with it, okay? So for every bit of light that you have that gets through entirely or almost entirely, you have one that's blocked or almost blocked. What do you think we should put in if we wanted to put in an average angle?
45.
45. Let's just put in 45. If all light is really in there in equal amounts, well, that means that it has just as much of a chance of being let through as being blocked. For an average angle of 45, cosine squared of 45 is a half. So if you put unpolarized light into a polarizer, it will reduce the intensity by half. And don't forget, what comes through is now polarized, because the only stuff that could get through is stuff that had either all or some along the transmission axis. So it also becomes linearly polarized now. So when you see me hold up this sheet, you can probably see when you look through it that things are dimmed a little bit. That's because the unpolarized light from the room is going through it and its intensity is being reduced by half. Okay? See that? Okay. So that's actually a way to polarize light in the first place, right? Is to send unpolarized light through a polarizer. Just for kicks here, now that I have it as polarized, let me go ahead and send it through a couple different options. So I'll splice them out here. So let me recopy my polarization, and I'll give you a couple different options. One of which is a polarizer where the transmission axis is aligned that same way. So how much of that light is going to get through the second polarizer? All of it. So if I have a second polarizer, okay, this dims the light significantly because it reduced the intensity by half. But if I put a second one in there, you might see it get a little dimmer. That's non-ideal behavior, but ideally it shouldn't make any difference. Okay? Okay? So now let's give another option. Let's put that second polarizer like that. How much is that going to make it through? None, because we're going perpendicular transmission axis. Let me show you. So here's where the first and second polarizers are aligned. Now let me rotate one of them. See the difference? Totally black. Now let me do a couple for the camera here. Transmission axis aligned.
Actually, you can't really see it. Pull them up to the side so they can see the whiteboard behind it. No. So like hold it to your shirt.
Oh, like this. All right, like this. Get a little closer. Okay, then I rotate it.
Nice.
How's that looking? Okay. All right, good. So you can see that. That is the idea behind polarizers. I guess let me do a numerical example while I'm at it, just kind of give you an idea. So how much you actually execute one of these in practice on the homework, so you have several of these. By the way, I also will post for you an applet which can do any combination of two polarizers. So you can rotate the transmission axes to each other, you can send in unpolarized light or already linearly polarized light in any orientation. It'll do anything you want. But let's take a look at how we might knock out a problem. So let's have a series of 3 polarizers. 1, 2. This one's going to be diagonal, so I'm going to have to tell you the angle here, 30 degrees from the vertical. So I can specify how diagonal is it. And then the last one, I'll have like this. So I guess that, just so that you don't mistake that as diagonal, that's going to be 90 degrees to the vertical. This is 0 degrees to the vertical. Okay? So that's a common thing, is that you're given a series of polarizers, and just to tell you how diagonal are they, you're given all of their angles from the vertical. Okay? Or, you know, all from the horizontal. Something to, so you can tell when they're diagonal and when they're not. Hopefully.
Yeah, looks like.
Fingers crossed. Man, hybrid classes are hard work. All right, so let's send in unpolarized light from the beginning. Let me do it in a different color, actually, just that way we can have a little more clarity, hopefully. So we'll send in unpolarized light of intensity I naught. And my question is simply going to be, I guess I should label this as an example, is what percentage of that can I be expected to get on the output? Now, one of the things that you might say, well, am I going to be able to get anything, because the first polarizer and the last polarizer seem to be mutually exclusive, right? You have this, anything that's getting through here is going to be vertical, but anything that needs to get through here is horizontal. So you might think, well, nothing's going to come out, but the middle polarizer is actually what saves us, okay, as I will show you. So first things first, what comes out? You learn that, first of all, if unpolarized light goes through a polarizer in any orientation, the intensity will be cut by half, and, of course, the outgoing light will now be polarized along the transmission axis that we just went through. So then it comes into the next one. It's like that. So that intensity, what angle does that polarization make with the, that incoming polarization make with this new transmission axis? 30 degrees. So we put in cosine squared of 30 is going to be the reduction of what went in, which was already half of the original. Which, by the way, if you compute what cosine squared of 30 is divided by 2, that's 0.375. So at this point, we only have 37.5% left of what went in originally. But it's not 0. And in fact, this is the part not to forget. Remember that the outgoing light goes parallel to the transmission axis. So what goes out is reduced, yes, but it's also rotated. And that's a good thing here because, of course, now there's something for that last polarizer to actually do, right? There's something for it to grab onto. So the middle polarizer, it reduced the intensity further, but it also rotated the polarization so that the last one has something to do, okay? Now here we have to be careful. This comes in like this. What angle should we use in the equation? Should we use 90? No? Should we use 30? What should we use? 60. So be really careful when you're doing these problems to measure the angle between the incoming polarization and the transmission axis. That may not be handed to you on a silver platter. You need to work it out sometimes. So we're going to have a further reduction of cosine squared of 60 with what went in, which what went in the first place was I naught over 2 cosine squared of 30. And now that's going to be reduced by cosine squared of 60 as well. Okay? So you can see that each polarizer appends its factor to the original. And if you work out what cosine squared of 30 times cosine squared of 60 over 2 is, that I believe should give you 0.094. So 9.4% of the original is left. But we do get something. And of course, as a reminder, we might draw that the outgoing intensity, while it is only 9.4% of the original, is horizontally polarized now, because that's the most recent thing that it exited. So if you don't believe me, let's try it. So we have, here are the two polarizers lined up. Now I can turn them sideways like this, and of course get nothing. So this right now would represent the first one and last one. And let me put one polarizer, that's why I have a third sheet, because I can put this in diagonally, and we will find that putting one in diagonally does mean that we will get something through. So let me put it in diagonally. And you should be able to see through where there are all the sheets. Can you sort of see through there? I don't know, that's not that bright, so it might not show up on camera, but I think in the room you should be able to see it.
Yeah.
Okay. So you can actually hopefully contrast, because this thing is square and it's in there diagonally. Of course, there are these corners here where there's only the original two, and those should be completely black, right? So the corners are completely black, and there should be a little bit more that can be displayed through the center part where there's all three of them, right? Okay, so I don't know if that's going to show up. Let me try to put this right there. I don't know if you could see that or not.
Try, if you lessen the angle, it'll let a little bit more light through.
Well, the problem is that if I'm actually putting this in not at 30 degrees, but at 45 degrees, which is what the most light will get through. The problem is if you rotate it to join either one of the first one or the last one,
It's darker.
it's going to just be a duplicate of the first one or last one. So if you should be able to see nothing here, nothing here, right? But when it's like that on a diagonal, you get something, right? So, so that right there, that's a little bit about how you calculate that stuff. Now, one of the biggest uses for this is you have these LCD displays, right? So like on a digital watch or something like that, a lot of gas stations, they have displays like this, okay? The way that they make these dark spots for numbers is there's the liquid crystals. That's what LCD stands for, liquid crystal display. There's these crystals where if you apply an electrical signal, you can get them to orient to either be clear, right, or make a number. That'd be like the number 1, okay? So these little cells that you can manipulate to either get them to go like this or like this. Now I want to point out, by the way, that even if we are talking about a part of the display that's not black, that's like this, you still have it going through a polarizer, so it's still polarized on the way out. So you're looking on that entire display, whether it's black or not, it's all polarized light. It's just that the parts where it's black is where the polarized light gets blocked by the second layer after it goes through the first. Okay? So what you can do with these guys, you can put a polarizer over them and you can cause them to turn black. So something like that. Okay? Because now you're of course blocking the stuff that wasn't blocked for the number, you're blocking it yourself. You see it kind of changing? Okay, so is this showing up on the, am I in the camera range?
Yeah, you're in the range.
It's just not showing up.
Doesn't look like it.
Okay. Well, if you want to get a really good display of this, if you are polarizing sunglasses, okay, your gas station is supposed to, theoretically, have it be that if you're holding the sunglasses on your face, you're supposed to see the display. You go like this, you can get it to turn black. Okay.
I think also like the sunroof from a car is polarized.
Mm-hmm.
I
Yep.
look at that and I see little splotches.
Yep. And sometimes even the displays in cars. There, you really want to make sure that it's such that when you're holding your head in a proper driving orientation, you can see it, but you can go like this, and you can get them to turn black. So the question is, of course, how do they know how to do that? Well, for reasons that I won't have a chance to get into today, the transmission axes on your sunglasses are always vertical. So if your sunglasses are polarized at all, which many are not, the cheaper you get, they're not polarized, they're just tinted. But if you get polarizing sunglasses, the transmission axes are always vertical. So they try to make sure that if it's not part of a number at the gas station, if it's just going through the part here, they try to make sure that that light coming to you is vertical, because then it'll get through your glasses. They can't control for you, of course, turning your head. Okay? And same thing with car displays, or even these digital wristwatches, right? They try to make it so that when you hold it like this, which is the proper way of looking at a watch, they try to make sure that the light coming to you is vertical so it gets to your sunglasses. You can go like this and get it to turn black. Either turn your head or turn your wrist. Okay? So we'll talk about next time, why is it that you want your polarizing sunglasses to have their transmission axis vertical? Because obviously there are applications in the real world that have nothing to do with the polarizer, this manufactured material. It turns out that when you reflect light off things, it tends to become polarized. So there are applications of this to the natural world as well. So let's knock off there for today and pick up next time.